value of the robust solution. Here we looked at the low variance and the high variance. So again, the green one, when you have perfect prediction, your demand is predicted perfectly with the real world. And here we are showing when you are activating the robust for the low variance and the high variance. But here, in this case here, we're doing it with omega equals 0. So we look at the risk neutral case. But still, if we do not include the variance, we see that you try to minimize based on the expected value of the performance. It helps here. This one here, when we start looking at different value, different omega, the weight of the variance term in the objective function. So clearly, if omega equals 0, this is the case that we are not including the variance term. And also when you go like it's great on the variance, right? I go W equal 5, or omega equal 5 times the variance 5 times, weight of 5 times the expected value. You can see things are bad. The thing that we see like with omega equals 0, for most of the horizon, the performance is better than when omega equals 0, right? So you see this here, in this case here, it's valuable to include with you the variance term in the. This is the one that we looked at also, is like two cases here. We look at the case when the different distributions. So this is a distribution of the real world, and this is actually this is a distribution of the one that we do the prediction, and this is the distribution that we do the real world. We tried two cases. Case when they are different distribution, but the range is similar. When a case here, the distributions are different, but the variance is different, right? The range of the distribution is different. You can also see the impact here. So it tells you like, at least if you cannot get the distribution, get a good idea about its range and the variability, right? Because if you don't have good information about the variability, you can see, you can compare the number here about 25,000 minutes, here 19,000 minutes. Of course, we can try other distributions. So for research extensions here, of course, we have not, even I'm saying this is real time, we have not done real time. We have not done it real time, but we mimic real time operation. We mimic real time operation here. So something that we need to focus on is how to really get it in real time, something like that, which could be possible if you look at the scheme of how we're doing it. I can do parallelization, right? I can take a scheme with an operation scenario and run it on different processors, right? So I can run many of them at the same time. This is something that hopefully we can look at. Of course, here we looked at scenarios, number of scenarios that we looked at. It was simple to say we have 5 scenarios, but in the real world, you could have many scenarios, right? So we're looking at some kind of like ideas for scenario reduction for stochastic optimization. People have done that. We can integrate some of these ideas here. Also, we need to look at, from a traveler point of view, how this improve when you do this robust traffic management scheme, how improve the reliability of the traveler, right? Here we look more from a system perspective. We can also try to see from a day-to-day DTA framework how this could help in improving the travel time reliability. Also, something that's new we're looking at here is like, if I'm looking at distributed DTA, distributed traffic management, and different operators managing different parts of the network, and each one trying to do robust, right? But can we collaborate together, right, to achieve higher level of robustness? This could be also another idea that we can look at. So this is, of course, this is the work. Is not mainly my work, right? This is always the student of our students, Hussein Hashimi. Hussein just graduated this fall. I don't know where he's going. He has 5 offers. He has not told me exactly where he's going. He's like, so we'll see where it's going. But also this project was partially funded by USDOT in collaboration with Bose and Hamilton on the area of active transportation demand management. So thank you all, and if there's any questions, I'll be glad.
Usually what they say about highways is you have more space, there is going to be more vehicles, and you say you haven't tested this in real time. So even if through some simulation you're going to free up some space and make it like most of the vehicles do fall through, there are going to be more vehicles added on. You have calculated the probability, but whatever the worst case scenario that follows along with it, maybe I'm not wording my question right.
Yeah. I agree with you. Like we see that, like if you're improving the performance of the facility, traffic will come, right? you can consider this here in many aspects. I consider it as a new operation scenario that might be generated with me. So when I'm being robust, I want to see like, yeah, this more demand will come. So I try to be considerate of that new demand will be generated. Right, but here we're looking at more of a short term. This is like operation, right? So I'm not looking at how the traffic will grow long term. Right? Yes.
I have two questions. First one, you could have done, is it true that you could have done the other way in the sense you would optimize for each scenario instead of scenario looking at expectation of all scenarios for each strategy? You could have done for each scenario what would be the optimal strategy. Just the other way. And that's one question. And the other question is, when you say the strategy, like the parent, each chromosome, how many variables do you have? Like how many control variables do you have?
Yeah. So
Because that would
let me answer the second question first. So again, when you are generating a scheme, you know how we build the chromosome here. So whenever we have an incident, right, we go and identify travel shed area around this incident. We go like 3 miles all over the area, and we take all the traffic lights in that area. I haven't shown it here, but this is usually we do. We define like the area, impacted area by the incident, and we take all the traffic lights, we take all the on-ramps that we can do, and this is how to find the length of the chromosome in terms of all the intersection, ramps, and all the dynamic message sites. Yeah, so we can think of a 3 miles. I don't have the number of how long it is, but this is how it is. For doing it the other way around, I'm not sure if it's correct, right? Because I'm looking for a scheme. I'm not looking for an operation scenario. I'm looking for the optimal scheme. I'm not looking for the operation scenario.
But you could implement whatever scheme depending on whatever scenario you see.
Implement the scheme.
Depending on what scenario you encounter.
Yeah, so in this case, yeah, maybe you can do something like that too. But it will not affect the performance of any way, right? Because you need to test for the combination of operation scenario with
Yes.
schemes, right?
And here, I don't have to.
Yeah, I know there's a class waiting to come in, so there's an idea. Dr. Abdelghany will be around if you